All right, so let's sort of hammer out an example here with full articulation so that we can get a feel for the process of dealing with a function where we're trying to compute the antiderivative, where we can see that the antiderivative, we can see where the function that we're trying to compute the antiderivative of has two bits of it that are related by derivative, but whenever we assign u to be the one and u prime to be its derivative, we don't get an exact, precise fit. We're close, we're off by a constant multiple. Well, here's the thing. Like, you can see by the fact that u is x cubed minus 2 that you could sub in u and get, well, I don't even need the parentheses whenever we sub in u. We could get u to the 7th and plug that in. Because, of course, if u is x cubed minus 2, then x cubed minus 2 to the 7th is u to the 7th. That's no sweat. That's just a mere swap of x cubed minus 2 for u. Okay, but now the issue is we can't take an integral here because we've got this integral being expressed both in terms of x and in terms of u. We need this thing to be expressed completely in terms of u with the differential du attached. So, man, how are we going to pull this off? Well, we need to get the x squared dx swapped out for something involved with u. Now, do we have x squared dx? No, we don't. But we know that 3x squared dx equals du. So be it, right? If we have 3x squared dx, but we want x squared, if we had x squared dx, we could just swap out directly. Well, that's fine because we can make x squared dx. We have a statement up here that relates to du and dx where we all, this is an equals, a statement of equality, since everything that's written here is two things that are equal to one another. Well, you could do the same thing to both sides and still get equal things back in return. So in particular, you could multiply both sides by a third and get a third du equals x squared dx. Because you see, what we have here is 3x squared. What we want is x squared. And if you have 3 times what you want, well, then you just divide by 3 or multiply by a third. Well, the long story short is now the x squared dx, which we were after, we have. We know precisely what x squared dx is. X squared dx is 1/3 du. We got this again by noticing that we didn't have just x squared dx, but x squared dx times 3. Well, we divided that 3 away, multiplied by a third, and now we have precisely what is in our function to integrate. And, well, applying the substitution here, then x squared dx could be replaced with 1/3 du. And now, how are we going to play ball here? Because we've got this 1/3 sort of hanging in there, and you might wonder, man, how am I going to sort of work with that? Remember this fact, which we've deduced previously, which is to say, if you think about constant multiples, when you take derivative, a constant multiple is unaffected by a derivative, which means a constant multiple would be unaffected by an antiderivative just as well. So the long story short is, whenever you have a constant that happens to be inside your integral that you're trying to compute the antiderivative of that function, you could just pull that constant out. So let's do that. Let's take the 1/3 and pull that 1/3 constant out. And now, at this point, breathe easy because look at all we have left. All we have left is u to the 7th inside our integral. All we have to take the antiderivative of is u to the 7th. And that is not hard because the integral of u to the 7th is 1/8 u to the 8th plus c. And well, this we can multiply out is what? 1/24 u to the 8th. And I tell you what, because think about this, this c is representing any possible constant. And if you take some arbitrary number and you multiply it by a third, you still get an arbitrary number. So let's just write that as, rather than writing that as a third c, which would be almost like unnecessarily cumbersome in statement, let's write that as just c, because again, any arbitrary number times a third is still just an arbitrary number. But now, what is the function that we're working with, which is the antiderivative of our function up above? This is 1/24 u to the 8th, but we don't want to leave it in this form because this form, while we've computed an integral and we've taken the antiderivative now. We've got a function whose derivative is what's above. The issue is we've had this written in terms of u. So let's write it back in terms of x by taking the u and replacing it with x cubed minus 2. And well, at this stage of the game, now we've certainly done it. And yeah, I say certainly done it. I mean, if you don't trust yourself and you want to check whether or not the function that came out of your antiderivative would in fact, when you take derivative, yield what was inside your original integral, you could run the computation here. You know the 1/24th would be unaffected. What I'm doing here is I'm taking a derivative. The 1/24th is going to be unaffected. 1/24th, okay? And then what else do we got? We want to take the derivative of this piece, but that piece is like a u to the 8th piece. So that would be 8u, 8u x cubed minus 2 to the 7th times the derivative of u. That would be the derivative of what's inside, and that would be 3x squared. And whenever you look at this expression and everything that's involved with it, you can see that you have a 3 and an 8 being multiplied and a 24 being divided away. And the long story short is that all boils down to the expression x squared times the quantity x cubed minus 2 to the 7th. And well, in short, this function that we produced as the antiderivative of the original function we were given is in fact the antiderivative, because when we take the derivative of it, we get precisely what was inside our original integral. And the long story short on how we did this was we first observed that we had an expression to integrate. We had a function that we wanted to find the antiderivative of, where two of the pieces of the function seem to be related by way of derivative. So we set u equal to, in this case, the x cubed bit, so that u prime could be the x squared bit. But however, whenever we did the actual derivative, we noticed that we were off by some multiple. The multiple was 3, we adjusted for that 3, we substituted improperly. We had that third there, but so we just pulled that out because any constant multiple goes through unaffected by derivative, goes through unaffected by antiderivative. So that constant multiple being drawn out now gives you something that you can compute more quickly, I guess, and easily. And well, because I mean, the derivative of a letter to any power, increase the power by 1, put that power in the denominator. And then this constant, we had the realization that, well, an arbitrary number times a third is still an arbitrary number. And the long story short is we got the results. The key step being taking the 3x squared dx, which we didn't have, and writing in the form of the x squared dx that we did have. Okay, so with that fully articulate explanation, let's hammer out these last 3 examples in the next video, and then we'll be sort of primed and ready to go with this idea.